Hello everyone, welcome to the lecture series on VLSI design. So in the previous lecture we had started with the module number 4 and we had looked into the switch level logic, that is our pass transistor logic and transmission gate logic. So how does these actually help us in subsystem design, that we had looked in our previous lecture. So in today's lecture we shall look into the gate logic. Okay. So gate logic can also be called as restoring logic. So what do you mean by a restoring logic? A restoring logic is the circuit, okay, designed so that even with an imperfect input pulse, a standard output occurs at the exit of each successive logic gate. That means it means that, okay, so imperfect input pulse in the sense, so usually we are having the voltage levels as logic 0 and then logic 1. For that particular thing we might be having the voltage levels for logic 0 will be a 0 volt and the voltage level for logic 1 will be, as a standard we will be considering it as a 5 volt. Okay, so imperfect logic in the sense v0l and then v0h or something, what we call it is nothing but we might not get the input pulse at exact 5 volt. There might be some variations that the input pulse might be varying from 0 to 4.2 volt, or it can be varying from 4.3 volt. So that variation will be there even though there is an imperfect input pulse for that particular input, but the output logic which will be produced at the output end, that will be a standard output. That means it will be from 0 to 5 volt itself. Okay, so that is why, that means at the input we were having there is a 0.7 or 0.8 volt difference, but that has been restored at the output. Okay, that is why gate logic is also called as what, it is also called as restoring logic. Okay, so in gate logic what actually we will be looking is that, so it is based on the general arrangement by the inverter circuits. As we know, our basic circuit is our inverter circuit, and based on our inverter circuit itself we will be making it as a standard or a reference circuit. Based on that we are going to define different NAND gate, NOR gate, and then different logic gates. Okay, so in this particular lecture we shall look into the inverter circuit first. Once we have finished with the inverter circuit, and we'll move on to NAND and then NOR. Okay, so in terms of subsystem design, what actually we'll be looking is that we'll be looking in terms of which type of logic, if we apply to our leaf cell, which logic will be better, that actually we will be looking in this particular lecture. So here basically we are looking in terms of CMOS logic, we are taking NMOS logic, and then we are considering BiCMOS logic. So these three technology logics, okay, that is CMOS, NMOS, and then BiCMOS, that we are going to take, and then making them as reference, we are going to differentiate which technology will be helpful for which particular gate, that we are going to look into this particular lecture. So we shall start off with our inverter. So as we know, let us look into inverter CMOS logic. This particular schematic diagram we had looked in, what we have looked in terms of in our module 2, how to draw the schematic, that also we had looked in module 2. And the similar stick diagram you can see at the right end, you can see over here the stick diagram. Okay, now if you look at this, our CMOS logic is nothing but complementary MOS logic. That means our pull-up region will be comprised of PMOS MOSFETs, okay, P MOSFETs, and the pull-down region will be N-type MOSFETs. Okay, so that is why it's being called as what, it's being called as complementary MOS circuits. Okay, now for this particular circuit, as we know, our the input what we are having, that should be a complemented form at the output. That means if I give 0 over here, my output should be 1, and if I give 1 and then my output should be 0. That is why. So how does a CMOS inverter works? Suppose if I give, let me take this thing over here. So if I take here 0, that means this particular transistor is in what state? It is open. The switch, it acts like an open switch, and this particular transistor will act like a closed switch, so that I'll be getting what? There is a continuous path from VDD to V out. So this will lead me to what? It will be leading me with 5 volt. That is nothing but logic 1. Okay. In the similar way, if you take in terms of if I take in terms of if I apply 1, then this particular transistor will be what? It is open switch, and then this particular transistor, it is closed switch, and then I'll be getting a perfect path which is connecting to ground. So this will be what? It is going to be ground. So what actually we'll be having? We'll be having 0 volt. So that is nothing but what? That it will be what? That will be my logic 0. So this is the basic working of our CMOS inverter. Now if you look at this over here in layout, so layout in the sense like we will be taking our PMOS, we have taken this substrate in terms of yellow color, and then for N type transistor we have taken the substrate in terms of green color. Okay, now whenever there is, as we have seen in terms of layout, whenever a substrate and then a polysilicon, what you can say, if they overlaps each other something like this, then there will be a formation of a transistor. This is what we had looked in while drawing the layout diagrams for our circuits which we had done in module number 2. Okay, now here you can observe there is a transistor formation over here, that is our PMOS transistor, and then here also there is a polysilicon overlapping on our P type substrate. So there is a formation of NMOS transistor over here. Since our inputs are shorted and then they have been given to V in, so here for this polysilicon we have shorted this particular polysilicon layer and then we have given it to V in over here. And then the output drains have the here you can see that for this PMOS the source has been connected to VDD. So here we have connected this to VDD, since VDD is a power supply. So here the supply voltage will be given in terms of metals. That's why here you can observe there is a metal layer which is in terms of blue color. In the similar fashion, we are having a metal which is connected to ground, and then we are having a metal stick diagram over here. Now if you look at this particular source is connected to VDD, and then both the drains are shorted, and then again I can tell the source of this is connected to ground, and then the drain, both the drains are shorted. Now you can observe over here, okay, the source is getting connected to VDD, and then here again the source is connected to ground. Both the drains are shorted, and then they have been taken in terms of what? They have been taken in terms of V out. Here you can observe the demarcation line. This line represents what? Um, the things which are above this line, what we can call them as what? What we can call them as pull up region, and then the region which is below demarcation line, that will be what? That will be pull down region. Okay, so this is all regarding our CMOS inverter. And one more thing what we need to observe is, if you look at our CMOS, the length is to width, okay, that will be what? 1:1 over for my PMOS, and then again for NMOS that will be 1:1. Okay, that's why they have mentioned it over here. That means 1:1 is nothing but we call it as what? We call it as length is to width ratio. Okay, so this represents what should be the length, and then this represents what should be the width. So for this CMOS, particular CMOS logic, we are having what? We have taken in terms of 1:1. That means both the transistor size, that is our PMOS size and the NMOS size, both are same. Okay, so now let us look in terms of next this thing. So let us move on to next. So that is our NMOS logic. Okay, so yeah, for NMOS logic, what we actually will be having is that we will be replacing our PMOS logic which was present in the pull-up region. That pull-up region will be replaced with a depletion mode NMOS transistor. Okay, so this particular pull-up region here, actually we were having what we were having a PMOS region, and then that has been replaced with my depletion mode NMOS region. So depletion mode NMOS region, in the sense what it will be having, it will, this particular transistor, whenever there is a logic 0 at the input, this particular transistor will be continuously on. So when this particular transistor gets turned off is that when we apply some positive voltage at the input. Okay, so that is why this will be continuously on, and then this will be, this is what, based on this V in, we are going to check whether our input is 0 or not. Okay, now let us see how actually this NMOS logic is going to work. Now if you take this, if I apply V in is equal to 0, okay, if I have taken it as 0, then my this NMOS transistor is in terms of open switch, and then since there is no voltage over here, though this particular transistor is continuously on, and this is the path what I'll be getting. So the V out what I'll be getting, that it will be 5 volt, so I'll be getting logic 1. Okay, in the similar fashion, if I apply 1 over here, this particular transistor is in open switch, and then I'll be getting a path which is connected to ground, so I'll be getting a value that is logic 0. Okay, now based on this, if you look at the stick diagram over here, since our this thing is NMOS transistor, here you can observe there is a substrate, and then there is a overlapping of polysilicon on the substrate, so there is a formation of transistor. Okay, but the gate, what you can observe is that the gate here, it is connected to where, it is connected to our V out, or the substrate which is getting connected to drain. Okay, so here you can observe the this thing is getting connected to our substrate over here. Okay, so here we are, here there is a formation of transistor, and then there is a connection what we are actually doing over here, and again here also there is a formation of transistor over here, and then that has been given to V in, and then the V out we have taken in terms of over here. Okay, again we are having a VDD which is in terms of connected in terms of metal, and then again we are having ground which is taken in terms of metal. Okay, but when you are going in terms of NMOS logic, the length or the pull up ratio and then pull down ratio, they are going to be different. As we had seen in CMOS logic, our pull up region length is to width ratio, and then pull down length is to width ratio. They were what? They were 1:1. Both were same. But when you take in terms of NMOS logic, the length is to width ratio is going to change. That why? Because uh, if we go in terms of 1:1 as in terms of both the transistor, then we won't get a proper output, or the switching, what we can say, that is the switching from logic 0 to logic 1 and then logic 1 to logic 0, that won't be proper. So in order to achieve the switching properly, that is, if you look at the graph what we are having, that will be in terms of what, our inverter graph, it will be in terms of like this. Here what we are having, that will be what, that will be our VDD by 2. Okay, so this particular graph or the DC transfer characteristics what we are having, that won't be achieved properly without changing the geometric conditions. That is why we need to change our geometric conditions so that we can achieve the graph or the DC transfer characteristics properly in order to compare, in order to achieve our inverter. Okay, now that is why here you can observe that for this particular this thing, the pull down region we have taken it as 1:1 itself, and the pull-up region we have taken it as 4:1. Okay, here here we can take based on the what might be the VDD voltage. Based on that we can achieve like whether we need to take 4:1 or whether we need to take 8:1. So that depends on what type of logic we are applying. Okay, now let us look into the thing how actually by varying the geometric dimensions how by varying the geometric dimensions in terms of transistor, how the power dissipation is going to be affected, that we are going to see in the next slide. Okay, so this is all regarding like the schematic and the layout. Now if you look at this, uh, here you can see an 8 is to the layout of 8 is to 1 NMOS inverter. If you look at the length of this, okay, it is 16 lambda. And then here there is a polysilicon. This represents my width, so width is only 2 lambda. And since my pull down region is 1:1, so I'll be having what the length and the width both are 2 lambda and then 2 lambda. Okay, so now if you look at this, the length has been increased over here in 8:1. So this is what this will give me a proper inverter circuit. But if I don't want to compromise in terms of this particular, if you look at this, this is what it is 16 lambda. So this particular logic might take me more number of area. So if I don't want to compromise in terms of area, then I can do the little changes in terms of the design so that I can achieve the similar inverter. And then if you look at the right diagram over here, so we have reduced the area in terms of since here it was 16 lambda, it has been reduced to 8 lambda. But this is what the changes what we have done to this particular thing is for what, this is for pull-up region. So in order to achieve inverter, so again what we'll be doing, we'll be making changes down to the pull down region as well. Okay, so pull down region we have increased the width of our pull down NMOS transistor. So we have increased our pull down region to 4 lambda over here. Now you can observe, what we can observe is that now if I had taken this as 8 lambda, okay, this particular this thing as 8 lambda itself, and then this particular transistor as 2 lambda across 2 lambda itself, then this particular logic what we are having, that will be what, that will be a 4:1 NMOS inverter. Okay, since I don't want 4:1, I want how by changing in terms of dimension or by changing the area, how it can affect in terms of power dissipation, that we are going to see. So here the same 8:1 NMOS inverter is being replicated in terms of a different logic by increasing the width of my pull down region and then by reducing the channel length by my pull up region, so that I can achieve inverter logic in terms of NMOS transistors. Okay, so let us look into the NMOS logic. So as we know, the impedance at pull up region is given by length by width. So length by width is what, for this particular thing, length is 16 and then width is 2. So 16 by 2, that will result me what, that will result me in 8. Okay, and then in the similar way, the total resistance occurred by this particular transistor, that is given by resistance pull up. So how can we achieve the resistance pull up? That will be done by impedance of pull up region into sheet resistance. Okay, so this particular topic we had studied how to calculate the sheet resistance, and then all those things we had done in terms of our module 2. Okay, as you can observe over here, the total resistance occurred at this particular transistor, that is resistance pull up, that is Z pull up into RS. So here the standard value of RS is 10 kilo ohm. So if you substitute those things, so 8 into 10k, that is 80 kilo ohm. So the total resistance offered by this particular transistor is 80 kilo ohm. Okay, in the similar way, so what is the resistance offered by this particular transistor? Again, if you take L by W, 2 lambda by 2 lambda, so that is 2 by 2, that will result me 1. and the sheet resistance, again the total resistance offered by this particular transistor is given by Z pull down into RS, so that is 1 into 10k, that will result in 10 kilo ohm. And then, as we have said, the power dissipation is given by what? It is given by V square by R. So here we are considering the power dissipated when the transistor is on. Okay, so V square divided by, so total resistance is, I need to consider the pull up resistance and then the pull down resistance. So here you can observe V square by R pull up plus R pull down. As we know, let us take our VDD as 5 volts, so 5 square divided by pull up is 80k and then pull down is 10k. Okay, so this is 80k and then this is 10k, and then the total resistance offered is 90k, and then 5 square will be 25. If I take 25 divided by 90,000, then I will be getting the total power dissipation will be 0.28 millivolt. If you take in terms of calculator, that calculator will give us in terms of 0.277777 recurring 7, so we have rounded off that to 0.28 millivolt. In the similar way, so the resistance offered by this particular 8:1 NMOS inverter is 0.28 millivolt. Let us look into the power dissipation occurred at the more circuit, that is our one more alternative 8:1 NMOS inverter. Okay, in the similar way, let us take in terms of pull up this thing. So 8 by 2, that will result in 4. So the total resistance pull up will be 4 into 10k, that will result in 40 kilo ohm. In the similar fashion, if you take in terms of our pull down region, that is the length pull down divided by width pull down, so 2 divided by 4, that will result in 0.5. so the total resistance across this particular transistor will be pull down is equal to Z pull down into RS. Since RS is 10k, so I'll be getting 5 kilo ohm. So the total power dissipated when the transistor is on, that is given by V square by pull up R pull up plus R pull down. Okay, now V square is 5 square, the pull up is 40 kilo ohm and then pull down is 5 kilo ohm. So 25 by 45k, that will result me 0.56 millivolt. As you can see in the previous slide, we had achieved the power dissipation of 0.28 millivolt, but when you take in terms of this particular thing, the value what we have achieved is 0.56 millivolt. So the power dissipation has been increased. Okay, by changing, see here, if we want to give up the area, if I want very less area, then the power dissipation will increase. If you don't want, if you are by this, what we can tell is that if we want the low power consumption device, then the area required for that way is going to increase. Okay, but if we don't want our this thing to be low power dissipation device, and I want very less area, then what I can do is I can go for these particular similar types of logics. Okay, but the power dissipation will be more. This is how, by varying the areas in terms of different transistor, how it is going to affect in terms of power dissipation, by just by considering area and power, that we can observe how differing in terms of area, how it is going to be reflect in terms of power dissipation, that we have seen over here. Okay, now this is what NMOS logic. So here what we are going to do is that, again, the L by W ratios are not at all same when it is compared to our CMOS logic. It is going to different for the pull down region as well as pull up region. Okay, now let us look into one more logic, that is our BiCMOS logic. Okay, so in BiCMOS logic, so BiCMOS is nothing but this particular thing here you can observe this is similar like our CMOS structure, where we are having a PMOS transistor over here and an NMOS transistor over here. Okay, and these things, they are being connected to what? They have been connected to our BJT. Okay, why these BJTs are used? Okay, or why these bipolar transistors are used is because the bipolar transistors are mainly used in terms of enhancing the output. Okay, as you can see, in terms of amplifying the circuits, most of the time we'll be going for what? We'll be going for these bipolar or junction transistors or BJTs. Why? Because if you look at the transfer characteristics, the transfer characteristics is somewhat like this. Okay, so that means what? It is exponentially increasing. Even if I give a small input voltage, then the output voltage will be what? Output voltage will be an amplified version. So if we are as we can see our transfer characteristics of our MOSFET, as we can see our MOSFET transfer characteristics somewhat lies over here. That means our current is what? Our current is becoming constant. Okay, so it is not going to increase exponentially. The current becomes constant. When the current becomes constant, the driving capability remains constant over here. Okay, if you want more driving capability, that means if you want, if the fan out is very much higher, at that time what we are going to do, we will be going for this BiCMOS logic. Okay, so these BiCMOS logic, that means the, as we are repeatedly telling that the fan out should be more. Whenever the fan out is more, then we are going for BiCMOS. So these BiCMOS logics where we can apply is that we will be applying these particular things in terms of what? In terms of our IO ports. Okay, so basically the whole driving is going to take place in terms of ports. So what we will be doing, this particular BiCMOS logic can be implemented in terms of IO ports. Okay, but the only drawback of BiCMOS logic is our stick diagrams or the layout. The formation of layout or the complexity of layout is very much higher when it is compared with the CMOS logic. Okay, so in order to produce this particular transistor, it becomes very much difficult. That is why people won't go for, suppose because whenever this thing is complex and the production cost increases, whenever the production cost increases, the product value is going to be increased or the price is going to be increased. Okay, when it comes to time to market or when it comes to marketing, the price what we are having, that should be as low as possible, so that we can achieve a good customer hold. When we are going for these such type of logics, then the uh, what we can tell, the production cost increases. When the production cost increases, the product value increases, or the product value is going to increase, then there will be a very less number of customers who are coming to buy our product. Okay, that is why people, they won't go for much. Whenever if we, the driving has to be done, then only they will be going for BiCMOS logic. So these are the different logics or the different techniques like NMOS and then PMOS. Let us look into the summary. So these are the schematics how we can achieve. As we said, there is no this thing over here in our this thing like CMOS. This thing is ratio L is to width ratio is 1 is to 1 itself. Okay, and then here we are going to change our length is to width ratio in order to achieve our inverter characteristics. And then this is mainly be there is no changes in terms of length is to width, but the VJTs are used in terms of what? These are used in terms of our driving modes. Okay, and then we have seen in terms of how varying our area in terms of length and width, how it is going to affect in terms of power dissipation, that we had looked in term by taking an example. Okay, so this is all related to what? This is all related to our inverter. So keeping these as our reference, schematics or reference design, inverter design, let us look into what? Let us look into our logic gates. So that is our NAND gate. Okay, as we have seen the CMOS NAND gate, you can observe over here parallel, and then NMOS will be series. If it is plus operation, PMOS will be series, and then NMOS will be parallel. So this is what we had seen in our module 2 when we are drawing our layouts, right? Or when we are drawing schematic for a much more complex equation or Boolean equation, how we have achieved. So that we had looked over here. So since it is a dot b whole bar, so what our PMOS will be in terms of parallel, and then NMOS will be in terms of series. Okay, now this is the layout for our NAND gate. You can observe there is a formation of transistor over here, and then there is a formation of transistor over here. Both the sources have been connected to VDD, so we have connected both the sources to VDD, and then there is a formation of transistor over here, and then there is formation of transistor over here, and then we have connected to B, and then here we have connected it to A. Okay, so here what we can observe is that since these are in series, that is why it is flowing something like this. That means it is getting connected in terms of series only. Okay, now here both the drains are shorted, so both the drains are shorted, and that particular drain is going to be output. So the shorted output we have taken in terms of our output line. And the source, again here what, again the drain has been connected to what? It has been connected to the output, so we are connecting it to the output over here. So this is what, this is our, again you can observe the demarcation line. So the region which is upward, our demarcation line, so that will be our pull up region, and then this is our pull down region. So let us look into how we can do this particular thing for our NMOS logic. NMOS, let me see. Yes, okay, here we can observe our NMOS logic. For NMOS logic, what we can have is that we are having two particular transistors which are connected in series. The pull-up region, as we know, the pull-up region is going to be replaced with what? It is going to be replaced with our depletion mode NMOS transistor. As now when you look in terms of our inverter, we were having something like this. We were having our pull down region where length is to width ratio was 1:1 only, and then this was 8:1. The pull up region was 8:1, and then here we were having 1:1 in terms of pull down. When we take in terms of what? When we take in terms of inverter. But if you look at the NAND logic, what we are having over here, it is 1:2, and then here it is 4:1. Okay, so why this particular length is to width has been changed when we look when we went for NAND logic, that we are going to see in the next slide. So let us look into that. So as we say, our you can observe the NMOS logic. So pull up region is being taken with what? It is being taken with one particular depletion mode NMOS transistor. But when you take in terms of pull down, if we had taken only a 2 input AND gate, then I will be requiring how many number of NMOS transistor? That will be 2. Okay, now if you take in terms of if you are having n number of inputs, or if you have if you are having 4 number of inputs, that let us take ABCD. So we'll be connecting 4 transistors in terms of series. Okay, now if I am having n number of inputs, then I'll be connecting n number of transistors which will be connecting in terms of series. Now this will affect us in terms of what? It will be affecting us in terms of our output, or the switching won't be proper. So in whenever there is no switching, proper switching, then we need to change what? We need to change our device geometry. So in order to make that thing, as you can see, when the number of inputs increases, the V out is not nearer to our ground. This particular path, what we are having over here, this particular path, it is going to increase. When this path is getting increased, V out is not equal to 0. The switching to 0 won't be that much easier. Okay, so as we said, for logic 0, V out should be less than or equal to Vt. That means in order to make these as 0, okay, so it should be less than Vt. That means it should be equal to 0.2 into Vtt. For if I want to be considering in terms of logic 0. Logic 1 does not have any what you can say, it does not have any this thing, since here we are having only one depletion mode NMOS region, and then that is connected to VDD. So that is not the case over here. The case is with the logic 0. Okay, now since we are, when the number of inputs are going to increase, this thing is going to increase, and then logic 0 we can consider when it is equal to 0.2 into VDD. If it is 5, then we can consider this thing as logic 0 even if we get what, even if we get 1 volt. So from that, what we can tell is VDD into our pull down divided by pull down plus pull up should be less than or equal to 0.2 into VDD. Okay, let us consider, let us neglect this VDD. Okay, let us remove these VDDs. Now if you look at this, if you look at the only the geometric dimensions, that is going to be defined in terms of this pull down and then pull up region. Okay, n pull down divided by n pull down plus z pull up should be less than or equal to what, less than or equal to our 0.2 into VDD. So here this thing, if you take, now if you take, when, how can I achieve 0.2? Okay, now here pull down, as we know our inverter, since it is if you look in terms of this thing, here the transistor is in terms of which are all are connected in terms of series. That means the pull down region what we are having in terms of our inverter, that has been connected in terms of series, that we can observe. Okay, but if you take in terms of 1:1 ratio, what we can achieve is, here you can observe 1:1. So 1 divided by 1 plus what should be my pull up region, so that I can achieve this 0.2. Okay, so here 1 divided by 1 plus 4, that means 1 by 5, that will result me what, that will result me in 0.2. This value I can achieve. Okay, so this value 0.2 I can achieve when I get this particular value. That means if I am having this thing, so that will result me what, that will result me in 1 by 5. So that is going to give me 0.2 volt. So if I take my Z pull up as 4, then I can achieve this particular voltage or this particular value. That is why our Z pull up by Z pull down ratio should be what, it should be 4:1. That is why our Z pull up region is 4:1, and then here it is going to be 1:2. Okay, so this is what, how we are going to calculate in terms of what, in terms of NAND gate logic. Again, when you look in terms of BiCMOS logic, we can observe our BiCMOS logic over here. This is what our circuit looks like in terms of BiCMOS. Again, BiCMOS is mainly used in terms of what, in terms of driving our driving our outputs. So these particular BiCMOS logics is going to be what, it is going to be useful only when we are driving more number of fan outs. So if the fan outs are more, then only we are going for BiCMOS. But as we know that the layout problems and then the layout design problems, it is going to be complex when we are going to in terms of BiCMOS logic. So this is the layout for BiCMOS logic. So as you can see how complex it is. Okay, so this is what our NAND gate. So NAND gate, in the sense, what we can tell is CMOS is what CMOS, again, here for NAND gate, CMOS is better when it is compared with NMOS logic and then BiCMOS logic. But the only problem what we can have in terms of CMOS logic will be what it will be. As you can see over here, there is a series of transistors over here. So whenever there is a series of transistors connected, the logic 0 part, what we can have, that we might get some delay. Okay, that means the 0, it has to pass through all these transistors which are connected in series. So the switching which is happening from 1 to 0, that might not appear. So that means what, there is not a sharp fall down, the fall time will be somewhat like this, because switching won't happen easily. Okay, so that might be the problem with what, the CMOS, but that problem we can overcome with the geometrical changes to our device structures. Okay, and when we looked into NMOS, again we were having only the problem with the pull down region. So the delay is going to increase. Whenever the delay is going to increase, we need to change our length is to width ratio in terms of NMOS logic. And then for sorry, this particular diagram is not correct for NAND gate. Okay, as we said, for PMOS, for BiCMOS, it is only meant for our driving, but the complexity increases in terms of layout designing. So this is all regarding what, this is all regarding our NAND gate. So let us look into NOR gate. As we know, for NOR gate, again, if you look at thing, so whenever we are having plus symbol, our PMOS will be in series and then our NMOS will be in parallel. As you can see, the PMOS transistors are connected in terms of series, and then our NMOS transistors are connected in terms of parallel over here. In the similar way, you can observe the stick diagram, the diffusion. This is similar like our NMOS logic, what we had seen in terms of our NAND gate. Okay, and then the source, both the sources are connected to ground and the drains are shorted. There is a formation of gate over here, there is a formation of gate over here, and there is one more formation of gate over here. And then we are having our demarcation line. So this will be our pull up region, and then this is going to be our pull down region. Now when it comes to NOR gate, what we can see is, in terms of NOR NMOS logic, we can observe that, see, in when we had taken our NAND logic, what problem we were having is, we were having problem with what, we were having problem with the pull down region. That means our transistors were connected in series. Okay, so by connecting the transistors in terms of series, we were not able to get the logic 0 properly, since the fall time is going to be increased. Okay, so that was the problem what we were having in terms of our NAND gate. But when you look in terms of NOR gate, so the NOR gate we can have only, since the transistors are connected in parallel, I can achieve the logic 0 easily. As we said, since whatever the pull-up region is going to be connected somewhat like this, so I'll be getting logic 1 easily. And since my transistors are connected in terms of series, even I can achieve my logic 0 very much easily. So here, if you look, if you compare this in terms of what, if you compare in terms of our CMOS, here you can observe the number of transistors are more. When the number of transistors are more, then the area is going to be increased. And here when it comes to NMOS logic, the number of transistors have been reduced and the area is also going to be reduced. Okay, and the problem, again, there is no problem with this logic 0 part. We can achieve this particular logic 0 easily, so that the switching will happen as normal as our inverter itself. So this is similar to our inverter logic. So the achieving can be done very much easily in terms of switching, and the area requirement is also very much less in terms of NOR. Okay, and the similar way our BiCMOS, again what, again it is only meant for the driving. Again the complexity increases, and the complexity increases, the production cost increases. So it is only meant for what? It is only meant in terms of IO ports. So this is what this the layout for NOR gate. So this is all regarding our lecture number 2, that is our gate level logic. So in gate level logic we looked into our inverter, we looked into our NAND gate, and then we looked into our NOR gate. So when it is done in terms of inverter, so for CMOS, these things are 1:1, and for NMOS logic we are changing the length is to width ratios in order to achieve our DC transfer characteristics properly. And then BiCMOS is only meant for what? It is only meant for the driving our outputs. So if you are having more number of fan nodes, then we will be going for BiCMOS. And then if we are going for what? If we are having in terms of, if you are going in terms of area, will be going for CMOS. And then if you are going in terms of power dissipation and all those things, then we'll be going for our NMOS. And then again, how to choose these in between these particular logics, that we have taken in terms of NAND gate and then NOR gate. So when you are going for NAND gate, we feel that the CMOS logic is better, but when it comes to NOR gate, we feel that our NMOS logic is better. Okay, so why we went for CMOS logic in terms of NAND gate is, when we go in terms of why don't we go for NMOS? Because the number of transistors are connected in series, then the fall time, the switching from 1 to 0, the fall time is going to be increased, then there won't be a proper switching. Okay, that is why we will be going in terms of what? Will be going in terms of CMOS logic when it is compared with NAND gate. But when it is compared with NOR gate, the pull down region what we are having, that pull down region is going to be in terms of connected in terms of parallel. So since it is connected in parallel, it is almost equal to what? It is almost equal to our inverter circuit. So better this thing we can achieve in terms of NOR gate when it is compared to NMOS logic. Okay, so keeping our inverter as reference, NAND gate we are going for CMOS, and then NOR gate we are going for NMOS. But when you are driving large fan nodes, or when you are making use of IO ports, then only we'll, for that particular thing only, we are going for BiCMOS. Why? The even it is having a good this thing, good transfer characteristics, and then higher what I can say, higher output this thing ratios, but still why we want why we are not going for BiCMOS? It is only because of the designing of layout becomes complex in terms of BiCMOS. Only that is the drawback in terms of BiCMOS logic. Okay, so this is all regarding our gate logic. So in the next lecture, we shall look into other forms of CMOS logic. What are the different forms of CMOS logic which are available in terms of our subsystem design, that we are going to see. And then we will be looking in terms of, if possible, we will be looking in terms of a parity generator example, how to design a parity generator, that we are going to see in the next lecture. Okay, thank you.